All right, so we are moving on to the final section of Chapter 6, which was about the Earth's internal processes. The last section of this chapter is dealing with volcanoes. So when we think of volcanoes, we think of these eruptions and we think of the lava. But where does that lava come from? Okay, when it's inside the Earth, the temperatures can reach up to 7,000 degrees Celsius. You would think that that would put most of the Earth in a liquid or even a gas state, but that's not the case. Most of the Earth still remains in a solid state due to the high pressure inside the Earth. It's got all this other stuff pushing in on it, and because of that, we have it as a solid state, even though the temperature is extremely hot. However, there are some areas of that asthenosphere. Remember which type of layer that is. Is it compositional or structural? In that asthenosphere, there are areas where melting does occur of that solid rock. And when melted rock is inside the Earth, it is called magma. So let's look a little bit closer at magma. Because magma is a liquid, it then becomes less dense as the rocks above it. And what do you remember about less dense things? What do less dense things want to do? Less dense things want to be forced upward. They want to rise so that magma finds the cracks in the lithosphere and starts going up towards the surface. If it cannot find cracks, it will create cracks or make the cracks bigger. And then when that magma reaches the Earth's surface, we have the start of a volcano. Once that magma has erupted out of the volcano and is on the Earth's surface, it is called lava. So there's the difference between magma and lava. If I was to draw a quick picture, if this is the surface of the Earth, let's draw some trees. Okay, and let's draw a volcano. Make it like this. Okay, we have this heating of rock that finds cracks up to the surface, and then when it's out here, okay, so we've got two areas. Okay, it's the same thing. Out here, when it is inside the Earth, it is called what? When it is on the Earth's surface, what is it called? So when that magma erupts and becomes lava, it occurs in two places. The first is hot spots, and the second is plate boundaries. Now, we've talked a lot about plate boundaries and what type of plate boundaries would cause volcanoes, but we haven't talked yet about hot spots. Hot spots are places in the mantle where the temperature is high enough to form magma. Okay, so what does this look like? Again, you have a plate. Let's make our plate. Okay. And let's just say this is completely over the ocean. Okay, no plate boundaries here. This is just one solid plate. However, you get places deep within the Earth that are extremely hot and can cause rock to melt. And that rock will then rise to the surface and cause volcanoes. Again, not at plate boundaries, but that's what a hot spot is. So when it erupts, what's in there? Well, we've got solids, we've got liquids, and we've got gases. So let's take a look at each part of it. First off, the solids are called pyroclasts. Okay, pyroclasts, if we break this word up into two, we get pyro and we get clasts. Pyro, probably a term you have heard before. It means fire. Clast means rocks. So pyroclasts are fire rocks. Back in the day, they thought volcanoes symbolized fire, so you get the term fire rocks. Okay. The solids can range in size from ash to very large rocks and boulders. Okay, a few weeks ago there was a volcanic eruption over in Europe somewhere. I remember the BBC had a reporter up there, and there was a bunch of tourists, and they were up walking around the volcano, and it erupted, and you can see these large rocks being ejected from the mouth of the volcano. One thing to know is depending on the size of the pyroclast is going to depend on how close it lands from the volcano. So let's get rid of my previous notes on this slide. Okay, if again, here's my volcano, okay, and we get this eruption. Okay, large rocks, okay, are going to end up nearby versus the ash that gets erupted. Okay, it is going to be transferred in the air, and it can go a very long way away. When Mount St. Helens erupted, late 70s, early 80s, can't remember exactly when, Mrs. Falk was not around yet, okay, that ash was seen all over the place. And the ash is what can be very disruptive to life on Earth because it gets carried into the air, it finds that jet stream, and it can be transferred for thousands of miles because it's light and it can be carried very easily. Gas that is in the eruption. We get water vapor. Water vapor itself, not a bad thing. We have water vapor in our air all the time. However, we have varying amounts of water vapor. Okay, it's what gives us our humidity. And then carbon dioxide. Again, carbon dioxide, not harmful as well because carbon dioxide is the gas that we breathe out, that plants breathe in. But when we have these two in such large quantities, we can actually get acids forming. And it's that potential for acid formation that can be harmful with the gases. The other part that we most associate with a volcanic eruption is the liquids. And the liquids flow across the Earth's surface as lava. The magmas, because they come from inside the Earth, can vary greatly in what they're composed of, what minerals make up those magmas. And the magmas ultimately are what give us our rocks, and it keeps that cycle going. But because the mineral composition can vary greatly, the physical properties of the magma, and then in turn lava when it hits the Earth's surface, can be really different. So we have to have a measurement to help us understand the liquid component of the eruption. And one measurement that we use to help us understand the liquid is viscosity. And viscosity is a measure of the resistance of a fluid to flow. So as viscosity increases, what does that mean? Okay, it means that the resistance is greater. So the resistance is greater. So is the magma or the lava, depending on where we're at, going to flow faster or slower when it has a high viscosity? Okay. And then depending on the composition and that viscosity is going to determine how eruptive that volcano is and ultimately what type of volcano we're even dealing with. So we've got a few different types of volcanoes, and they are classified based on shape, size, and materials that compose them. So there's three things that really compose those volcanoes and what help us give us the different types. Three types of volcanoes: cinder cone, shield, and composite. So let's take a look at each one of these. First is cinder cone. Cinder cone volcanoes come about when the primary eruptive products are large fragments of solid materials. Okay? When you have that, cinder cone volcanoes are formed. Cinder cone volcanoes tend to be really small. Okay, we're talking hundreds of meters. When you think of a volcano, you're not thinking of a cinder cone volcano. That image that you get in your head of the big giant mountain-like volcano is not a cinder cone volcano. Cinder cone volcanoes are very small. Okay. Cinder cone volcanoes are often called parasitic cones because they are actually found on larger mountains such as Mount Kilimanjaro. So what does this cinder cone parasitic volcano look like? So we have our volcano here, and we have our pipe where that magma is coming up and then erupting up here of the main volcano. Well, off to the side, you may get offshoots, and you might start to get little volcanoes forming. Okay, feeding off of that much larger. These are your parasitic cinder cone volcanoes. Next type of volcano is a shield volcano. Shield volcanoes form from high temperature fluid basaltic lava. Okay, so very high, very fluid means that it is thin and it flows very quickly. So does it have a high viscosity or a low viscosity? Another clue here on shield volcanoes is this basaltic lava. Basaltic lava is lava typically found in the ocean because the ocean seafloor is composed of a rock called basalt, where continental crust is formed from granite. So this basaltic lava is formed usually in the ocean floor. Because it's fluid and it has a low viscosity, so it flows very easily, it can spread out very quickly. So the type of volcanoes that we get here are very flat and very broad. But they build up over time because as that lava cools, you get another layer formed on top of it. An example of shield volcanoes is the Hawaiian Islands. What does this look like then? So you've got your ocean floor here. Okay, and all here is water. Okay, until you get to your ocean surface. What's going on underneath? You have your crack in the earth, okay, that starts to form and spread out very thin. And then you get more coming up that builds on top of it. And then you get more that builds on top of it. And this process keeps going. You get these very thin layers built one on top of the other, and eventually you reach sea level and you start to get it built up. Okay, but no, here, my picture here, this could be 25 kilometers across. Okay, so these are very thin but very wide layers. Final type of volcano is composite volcanoes. And when you think of a volcano, this is what you're ultimately thinking of. When you think of those big eruptions, you think of the movies, you think of pictures that you have seen in the past, you think of the composite volcanoes. Okay, these are rich in silica. Silica is a mineral that makes magma sticky. So it gives it a higher viscosity. So is it going to flow quick or is it going to flow slowly? Composite volcanoes are usually found at convergent boundaries. Okay. Rock gets pushed down at the convergent boundaries, starts to melt, and makes its way to the surface. So these are alternating layers, but because it's sticky, it doesn't flow quickly, so it doesn't spread out thin. Instead, it starts to build itself up very high. Your example here is Mount Rainier. Let's look at what this looks like. So we've got really two crusts here. We've got our continental crust and we've got our oceanic crust. And this oceanic crust gets forced downward at the convergent boundaries. Remember, when it gets forced downward, it starts to heat up and melt, and it wants to rise to the surface. Okay, so it finds those cracks. As it finds its cracks, it starts to form a volcano. But because it's sticky, it doesn't spread out very far. And then it erupts again, and again, and again, and you start to get this mountainous peak that forms. Okay, so when you see these big mountainous volcanoes, you have a pretty good idea: convergent plate boundaries, and they're composite volcanoes. So here's all of this really put together: the composition, the silica content, the gas content, the viscosity, and the volcano type. So let's look at a few trends here. You've got your basaltic, your andesitic, and rhyolitic compositions. Those are minerals. Those help us identify what kind of rocks are also going to be formed. I'm not concerned, you guys know that composition. Silica content, though, you need to know. Okay? Think of silica as sticky. So the more silica, the stickier that magma and that lava is, so the slower it's going to flow. Gas content, you need to know. Gas content, how much air is in there? When something has a bunch of air bubbles, it usually doesn't flow as easily. Think of pancake batter. Okay, when pancake batter has a lot of air, you get these fluffy pancakes, but that batter doesn't spread out very much compared to crepe batter. Crepe batter doesn't have air in it, and because of that, it flows and spreads out on your pan and forms a very thin crepe. Viscosity, you can see there how those are connected, which you do need to know, and you do need to know your volcanic types. Okay. Be ready for lab tomorrow. Get that entry ticket done, and if you have any questions, please let me know. Have a great day.